Welcome to Lecture 9 in Mathematical Foundations of Robotics. This lecture is devoted to revise some concepts on elementary functions and applying those concepts to solution of exercise. So let's start with the first exercise. Determine the number of solutions of the equation 2 to the x minus 1 absolute value equal to lambda, with lambda being a real parameter. In other words, what we're trying to see here is how many solutions does this equation have for each possible value of lambda. One way of approaching the problem would be to study the function f of x equal to the absolute value of 2 to the x minus 1 and see when this function intersects a horizontal line at lambda. So let's start by drawing the graph of this function, and we'll start by drawing 2 to the x, which we know is just an exponential function crossing the y-axis at 1 and is strictly increasing. Now we need to shift this graph downward by 1. So the result would be a new graph This is just the function 2 to the x minus 1 after a vertical shift downward of 1, which is crossing now at 0. But we then now need to apply the absolute value. So the final graph of the function will be this. So this will be f of x equal to the absolute value of 2 to the x minus 1. Now that we have this graph, we can draw many horizontal lines for different values of lambda. For example, if lambda is less than 0, we see that we don't have any intersection with the graph. So we can say that there will be 0 solutions for lambda that belongs to minus infinity 0. If instead lambda is crossing exactly at 0, or if lambda is crossing at the value of lambda larger than 1, we will have two possible intersections. So we can say that there will be one solution for lambda that belongs to the union of 0 and the set 1 plus infinity, including lambda, because in fact if we consider this line, there will be only one intersection on the right branch of the function. Finally, we see that there will be two solutions for lambda that belongs to the interval 0, 1. Right, so this concludes the analysis. Let's solve now a similar problem, exercise 2, where we need to determine now the number of solutions of the equation x plus 2 absolute value plus x plus 3 absolute value equal lambda, as always with the lambda as a parameter. Same problem, same approach. We will study the function f of x equal to x plus 2 plus x plus 3. Now we have two absolute values. To get rid of the absolute values, we need to divide the interval of definition in subintervals so that we can study the sign of each and every term of the function. And we immediately see that if x is less than or equal to minus 3, well, f of x will be equal to minus x minus 2 minus x minus 3. In fact, the two terms, these terms x plus 2 and x plus 3 are both negative, so applying the absolute value consists just in inverting the sign, and so we get minus 2x minus 5. If x is in between minus 3 and minus 2, then f of x, well, in this case, only x plus 2 will be negative, right? So we have x plus 3 minus x minus 2, which is equal to 1, so in this case it is a constant. If instead x is to the left of minus 3, then, if x is to the right of minus 2, well, in this case both elements, both the terms are positive, so we have x plus 2 plus x plus 3, which gives 2x plus 5. So finally, we can draw the function, and we can identify minus 1, minus 2, minus 3 here, and we immediately see that in the segment from minus 3 to minus 2, this function is constant and it's equal to 1, while to the right of minus 2 or to the left of minus 3, we have a slope respectively of plus 2 and minus 2. And that means that this point, because moving from minus 2 to minus 1, we are moving of 1 unit to the right, so we would expect this point to be 2 times the one achieved at minus 2, which means 3, and moving again of 1 unit from minus 1 to 0, clearly we have another 2 added, so this will amount to 5. Similarly, if we go to the left, we will have minus 4 and minus 5. At minus 5, since because of the symmetry of the function, we will achieve once again 5. So this is the graph of the function. Now we need to draw lines. We need to draw horizontal lines corresponding to possible values of lambda. Now we see that for lambda less than 1, there will be no intersection. So we can immediately write that there will be 0 solutions for lambda that belongs to minus infinity 1. If instead we have a line that is crossing the y-axis for a value larger than 1, we will have 2 intersections, 1 and 2, right? So we have 2 solutions for lambda that belongs to the interval 1 plus infinity. And finally, if instead we have a line that is just crossing the y-axis at 1, well, we have a continuous intersection, namely the segment that goes from -3 to -2. So that implies that there will be infinitely many solutions for lambda that belongs to the set 1, and all these solutions are the infinitely many points of this segment. Good. As another interesting observation regarding this function, we could try to evaluate the image and pre-image of some intervals. So let's say that we have our graph x and y here. So we have -1, -2, -3, -4, and we have this function, and let's say that this is -5, and we already know that -5 identifies, well, the image of -5 is captured by the left branch of the function, and the corresponding y is going to be 5. And let's say, for example, that we want to identify the image f of a specific interval -5, -1. Well, the procedure for finding the image of the interval is, the first step, identify on the x-axis the interval. And this interval is from -5 to -1. Then we need to go on the graph and identify the corresponding piece of the graph. And the corresponding piece of the graph, of course, is this one. And, well, we need to also find this, but we know that this is 3, so there will be also this part of the graph. Finally, we need to project this part of the graph on the y-axis. And what happens is that, remember that this is 1, so the projection identifies this interval. So we have 1, 5. Similarly, we could find the pre-image of an interval like -5, 1, for example, -5, 1. Okay, so that means that we are considering now from -5 to 1. So this time we need to start from the y-axis, and this is the interval that we are considering, and we need to go to the graph now that corresponds to this interval, but the only part of the graph that corresponds to this is the one that corresponds to 1, and projecting this on the x-axis gives us the interval -3, -2. Okay, good. Let's move now to a different problem, more theoretical in nature. So let's say that we want to solve the following problem. Find the function f from a to b, non-invertible, for which there exists a function g that goes from b to a such that for this function g of f of a is equal to a for every element in capital A. Okay, so you might remember that this is just half of the requirements for an invertible functions. In fact, in general, if we have a function f from a to b, which is invertible, well, invertible means two things: to be injective and surjective. So moving from A to B, an invertible function looks like something like this. So this is f, and of course the inverse would be simply that. So this would be g, the inverse function. Now, for such a function, we know that two conditions holds. G of f of a is equal to a for every a in capital A, and f of g of b would be equal to b for every b in B. Now, we are neglecting this second condition in our situation. We are just considering the first one. So, in other words, we are picking a single element of A. We are then hitting the corresponding element of capital B by F, and then we are going back through G to the initial element. So this is the only condition that we want to find. Okay, so we need now to understand which of these two conditions, injectivity and surjectivity, can still hold if we want to meet this one condition. Now, the thing is this, that suppose that we have f not injective. Let's consider this first case. Okay, it might be that f is not injective, so we may have a situation like moving from A to B. We take two different elements, A1 and A2, and these two elements have the same image through f. Well, but because now we know that there will be a g function defined on B, well, only one of these two elements can be hit by g. So when we apply g to this element of B, we can reach only one of the two elements of A. So that means that there will be something in A that will never be reached by the function g. Okay, and which is impossible, because that is the original condition for g. The original condition says that g can reach any possible element of A. So clearly we now know that f must be injective, but that implies that f cannot be surjective, just because we know that one of these two conditions must be missed, okay, because we know that f is not going to be invertible. Okay, so let's see how this function f might look like. So if this is A, this is B, we start from elements of A, and with these arrows that represent f, we can reach points of B, and there will be an inverse, well, not an inverse, but a function g defined on capital B that will be able to reach some of these elements. But because f is not surjective, there should be at least one point in B which is not reached by f, but where g is defined so that finally g, for example, can reach from that point one element of A. So this is how the function f and g might look like. Let's now attempt to build the composed function g composed f. Now, this g composed f goes from A to A. We would like to study this function and see what kind of properties this function have. For example, is this function surjective or is this function injective? Let's start with the injectivity. Let's see if this function is injective. Well, injective means that if we pick two different elements in A, for example, these two elements, this one and this one, we end up in two different elements after applying g composed f. Let's see. So if we apply f to the first element, we end up here, and applying g we come back, so we have exactly this element. So in other words, if we apply f to this element, we end up in this element B. Now we apply g and we go back to this element. So this is one possibility. Now let's see what happens if we apply g composed f to another element. For example, this one. If we apply f first, well, we know that we will end up into this point. And now we go back by g on the same point. So yes, for every element of A, we come back exactly to that element. So we can say that the function is injective. Second question is this function surjective? Surjective means that we can reach any possible element of capital A, which implies that there is no element in capital A that cannot be reached by g composed f. But this is of course the case because f is being defined over the entire set A. So after applying g, we go back exactly to the element where f were originating from. So this function is injective and surjective. In other words, this function is invertible. Let's see if we can also do the same thing with f composed g. So we have A here, we have B here, and we know that f will be a function like this. This will be the f function. And now we know that there will be also some element that is not reached by f, but then we can apply g to B, and in particular this element will end up in some element of A. Okay, and we want to now study the function f composed g, which is a function that goes from B to B. So for example, we'll start with this element, and applying g one time we get to this point here in A, and then applying f back again we come back exactly to the same element. So apparently this seems to be a function that might be injective, but let's check what happens, for example, for this element and this other element, because G is defined in both of these elements. So if we start with this element, we apply G one time, we go back to this point, and then applying F, we come back to the original point in B. Let's see what happens now if we pick a different element, this element here. Well, applying G, we end up into this element, but now applying F, we go to a different element. So this function is not injective. So definitely this function cannot be invertible. Let's see if this function is surjective. Well, surjective means that I should be able to reach any possible element in B. But we have just seen that this specific element cannot be reached in any way. So this function is not surjective. So it is neither injective nor surjective. Good. To give you an example of a similar function with the same properties, let's consider the case where, remember that we have defined f from a to b, but let's say that f goes from n to n, natural number to natural numbers. For example, this function can be expressed as f of n equal to n plus 1 for every natural numbers n. So this, in other words, this is just a forward shift by 1, okay? By 1. So in other words, you pick any number n, and this function is projecting this into n plus 1. So for every number n, the function is forward shifting by 1 the number. Okay? Well, this function can be, we can easily prove that this function is injective. Why is this function injective? Well, because of course, if you pick two different numbers, okay, so if we have n1 different from n2, what happens? That f of n1 will be equal to n1 plus 1. F of n2 will be n2 plus 1, but they are different one from each other. F of n1 is different from f of n2. So clearly this proves that the function is injective. However, this function is not surjective. Let me prove this statement. Why am I saying this? I am saying that the function is not surjective because there would be at least one element of the natural number which cannot be reached by any arrow. And in fact, there will be there is no n into the natural numbers such that f of n will be equal to 0. Okay, so the 0 is never reached in any case. So this function is not surjective. So it is just like an example of the function that we have given above. A function that is injective and not surjective. Let's see what is the function g, okay, g of n, that can satisfy the only condition that we want to satisfy is that basically g of f of n would be equal to n. Okay, well, this function is easily found as n minus 1 if n is larger than or equal to 1. But of course this still has a problem, because we need to find what happens if n is equal to 0, because of course we cannot apply n minus 1 to 0. We would end up in the negative natural numbers which do not belong to n. Okay, and we want, basically remember that we want g to be another function from the natural number to the natural numbers. But we can easily fix this. We can give any possible number, for example 20, 24. Okay, so this function actually is able to, if I evaluate g of f of n, well, that implies g of n plus 1, but this is just equal to n. So this simply proves that such a function is easily to be determined. Okay, and also we can see that if we do g composed f, okay, that again is a function from n to n, well, this function is bijective, and this is easy to be proved by just looking back at the proof that we have done before. Okay, so let's change now attention. Let's move to different examples, to a different exercise. Let's go exercise number 4, and let's try to apply what we have learned in terms of inverse trigonometric functions. So let's try to solve the equation arc cosine of 3x plus 1 equal to arc cosine of 2x plus 3. Okay. Now remember the shape of the arc cosine function. If we have x here, we have arc cosine of x here, and we know that this function is defined in the interval minus 1, 1, and the shape will be something like this being pi and this being pi over 2. Okay, so this is the arc cosine function. Now the question is, can we just get rid of the arc cosine function? Now to do this, we know that we must prove that the arc cosine function is injective, but we know that this is injective, right? Because moving from minus 1 to 1, the function arc cosine of x is strictly decreasing. So this is a strictly decreasing function. It is injective. So arc cosine of x is strictly decreasing in minus 1, 1. So it is injective, which means that we can get rid of arc cosine in the equation. In other words, we can solve, instead of having arc cosine on both sides, we can just solve 3x plus 1 equal to 2x plus 3. Unfortunately, when solving this equation, we can easily find that x is equal to 2, right? Which is not acceptable, because this is not acceptable because x equal to 2 does not belong to the interval minus 1, 1. So clearly this is just an impossible equation. So this is impossible. Okay. So let's see what happens if instead of applying the arc cosine, we would just have this equation: logarithm base 11 of 3x plus 1 equal to the logarithm base 11 of 2x plus 3. And we know that the logarithm base 11 of x will be a strictly increasing function crossing the x-axis at 1. Now, the logarithm base 11 is defined only for x larger than 0. So if we want to solve the equation logarithm base 11 of 3x plus 1 equal to logarithm base 11 of 2x plus 3, we can get rid of the logarithm on both sides as long as the arguments of the logarithms both sides are larger than 0. So we can write 3x plus 1 equal to 2x plus 3, and then finally solve for x equal 2. But then we need to check that 3x plus 1 is larger than 0 and 2x plus 3 is larger than 0. And in fact, we can do this, right? We can say that this is indeed a solution. Let's now try to apply to the same terms 3x plus 1 and 2x plus 3 the arctangent. Okay, so let's try to solve now the equation arctangent of 3x plus 1 equal to arctangent of 2x plus 3. And let's draw the arctangent of x, and we know that this is the graph taking values between minus pi over 2 and pi over 2 for every possible x. So in this case we have a strictly increasing function defined for every x. This is defined for every x into the real numbers. So in this case we can just get rid immediately of the arctangent, because we know that the function is strictly increasing, therefore it is injective, so we can immediately say that x equal to 2 is going to be a solution. Okay, let's now pass to another exercise. This was exercise 4, let's say exercise 5, and let's make a compound trigonometric function f of x equal to the cosine of sine of x. Now, this compound function is clearly a periodic function because it is made of two periodic functions, and since both sine of x and cosine of x have a period to pi, we can say that certainly this function is periodic with a period to pi, even if we don't know that this is the minimum period. So this might not necessarily the minimum period. And so this is the first thing to prove, okay? And the second thing that we would like to prove is that this function is even, okay? Now, So let's say that this is one thing A and B. Let's first prove A. So let's first prove that f of x is a periodic function. Well, the thing is this, that in general, we can say that in general, if we consider a function h of x periodic with the period t, any compound function g of h of x is periodic with period t as well, even if this is not necessarily the minimum period. I want to prove this now. So the proof is that we should evaluate g of h of x plus capital T, okay? Because this is, let me write this down. We can say that the compound function g compound h evaluated at x plus capital T is g of h x plus capital T. But because of the periodicity of h, we know that this is equal to g of h of x, which is exactly g compound h evaluated at x. So this finally proves that the compound function g compound h is periodic with the period t. Now, in our specific case for f of x, we can see that f of x has minimum period t equal to pi, not to pi. Okay, so let's prove this. In fact, we say that f of x plus pi is equal to the cosine of sine of x plus pi, which is cosine of minus sine of x. But because cosine is an even function, we know that this is just equal to the cosine of sine of x, which is exactly f of x. So this proves that pi is the period of this compound function. Now, the second thing we want to prove is that f of x is even. In other words, we want to prove that f of minus x is equal to f of x. Now, f of minus x, so this is the proof, f of minus x is equal to the cosine of sine of minus x. But because sine is an odd function, this is equal to the cosine of minus sine of x. And because the cosine is an even function, that is equal to cosine of sine of x, which is equal to f of x. And this concludes the proof. Okay? We might be tempted to generalize this result. In general, if we have, let's say, two functions, let's say that f is even and g is even, then we can certainly say that g compound f is even. Okay, let's give the proof to the right. Okay, proof of this is that, or let me put the proof here. So this is the first statement. We want to prove that G compound f of minus x, so this is basically G of f of minus x, but because f is even, this is equal to G of f of x, which is exactly G compound f of x. So this concludes the proof. What if f is even and G is odd? Well, we can conclude that G compound f is even again. Let's prove this other statement. So we have that G compound f of minus x is equal to G of f of minus x, but again, because f is even, this is equal to G of f of x, and again we have the proof. So the fact that f is even makes the whole compound function even in any case. So we can conclude this too, saying that if f is even for every G compound f is even. Okay, let's consider now the case where f is odd and G is even. What can we say about G compound f? Well, we would say that G compound f is even. Let's prove this. We have G compound f of minus x, which is G of f of minus x. But now f is odd, so this is equal to G of minus f of x. But because G is even, clearly this is once again equal to G of f of x. So the evenness of one of the two functions basically makes the whole compound function even, both if f is the only even function or G is the only even function. Let's now look at the last possibility, f odd and G odd. What can we say about G compound f? Well, G compound f in this case is odd, so this is the only possibility to have a compound function is odd. Both of them must be odd. Okay, let's prove this. We want to find G compound f of minus x, which is equal to G of f of minus x. But now this is equal to G of minus f of x, because f is odd, and because G is odd, this is equal to minus G of f of x, which is minus G compound f of x. And this concludes the proof.